Welcome back to Pre-Calculus, which is actually calculus. We're in section 3.2, and we're going to be talking about differentiability, or another way to think of differentiability is how to figure out whether or not a derivative is continuous. So if you remember, derivatives are very, very similar to our limits and our tangent slopes. Derivatives are similar to tangent slopes in that they are, in fact, like the tangent line, and they're similar to limits in how we compute them. Because we saw in the last section we can compute left-handed derivatives, right-handed derivatives. What differentiability is talking about, the best way to explain it to your mind right now, what you already know, is that if we have a left and right-hand limit, and the left-hand limit does not match the right-hand limit, then the limit fails to exist at the point of that line. So like if we were going to do a jump discontinuity on a function like this, at this point, the limit would fail to exist. And the same goes for differentiability. A function is not differentiable if the left and right hand derivatives do not match. Now, there's some special instances where that happens, and I've done some drawings on the textbook to kind of explain this. So it's talking about how f prime of a, or how the derivative of a might fail to exist. So this is using the secant definition, where we're doing infinitesimal add and infinitesimal amount subtracted on either sides of the point. So using this definition, if we run across a corner, right, where the one-sided derivatives differ, it would fail to exist. I'm kind of gonna trace this with my ruler, right? So what we can see here is as we approach the left-hand side, right, the derivative as we approach 0 is going to be a slant like that. So it's going to have a negative slope. So the slope would be a negative tangent line. As we approach from the right-hand side, it would be a positive tangent line. So in this case, we have opposite slopes. And I've kind of written it there. Wait, I forgot I'm supposed to use the zoom button. But what oh no, this is the worst time for my program to freeze. I need to use the zoom button, and the zoom button's frozen. Why can't I see it? This is weird. Ha, got it. All right. Let's just closer, enhance. All right. So right here we can see the slope. This one has a slope of -1. This one has a slope of +1. So if we were to compute the derivative, the left-hand derivative or the right-hand derivative, they would not match, meaning this is not differentiable. The key thing there is whenever you see a corner. So corners are not differentiable. Let's go to the next one. This is called a cusp, right? So what we see here with these slopes is as we approach the left, right, the tangent slope drastically turns very sharply right as we get close to 0, right? And it seems like this slope is moving towards negative infinity, right, which would be a vertical slope, which is what it seems to approach right before it gets to 0. If we approach from the right hand, we see the same thing. The slope turns and it's practically positive infinity at that point. So a cusp, so where we have two curves that meet sharply, then we also fail to have a derivative. Or sorry, we fail to have it fails to have a derivative at that point, which means it's not differentiable. Okay, next one. I actually had to draw another sketch on this page. So this is where from both sides it seems to meet infinity. So pretty much any time your slope seems to go straight vertical, your function is probably not differentiable at that point, or it ceases to be continuous, which is a little bit tricky because when we were learning about continuity, we're like, hey, continuity is when we can draw a straight line. The trouble here is we have to think about the graph of the derivative at this point as opposed to the graph of the function. So this is the graph of the function, and we can see as we go from this side, it would end up being positive infinity. From that side, if we go from this side, it would still be positive infinity. However, that positive infinity is not differentiable, meaning that the graph of the derivative does not have continuity. I'll show you what that looks like on a whiteboard, right? Oh, I forgot I need to zoom out. All right, so this little graph, if we were to sketch the graph of the derivative, we can see that right at 0, the right-hand side seems to go towards positive infinity, and the left-hand side also goes towards positive infinity. If we look at the graph over here, on the left-hand side, it's practically, as we start off from that side, it's practically 0, right? We're practically horizontal, so we're starting off at 0 on this side, and then it's going to slowly rise until it gets to right before 0, and it's going to drastically rise to infinity. Same thing on the right side, it's practically 0, and then it rises again until it gets to infinity. So we're starting at practically 0. And this is what the graph of the derivative would look like. Now what we can see is there's a vertical asymptote here, meaning there is no derivative at 0, and that's how it fails to be continuous, right? So if we were to try to draw this with one line, we can't, because we would never be able to come back down and draw the right side. Differentiability, that's how differentiability can be thought of as continuity. So if the graph of the derivative is continuous, it is differentiable, right? So that's one case. We could have it where it curves like this. We could also have the opposite, where if both slopes are negative infinity, right? So if the curve goes drastically straight down like that, where we've got a negative infinity from the left and a negative infinity from the right, then the curve would also fail to be differentiable. All right, so hopefully these drawings are starting to help out, and definitely if you really got through that part of understanding the graph of the derivative in the previous section, that is also going to help you out here. So last one is a jump discontinuity. This one's pretty easy. Same thing. And the fun thing about these functions is they look pretty similar to their derivative graphs. So this discontinuity is going to show the one-side derivative is not matching, and that's pretty easy to see. As we approach from the left, it looks like the derivative is going to be -1. As we approach from the right, it looks like it's going to be +1, right? Or wait, sorry, did I say the graph of the derivative looked the same? No, it would not look the same. So this one's a little bit tricky because the left and right hand don't match. So what this one would look like is, as we approach the left-hand side, the graph of the derivative would be about 0. And then something happens here where we've got a hole, and then the graph in the right hand exists. So from the right hand, the derivative exists, but from the left hand it doesn't. So at 0, there is no derivative at that point, right? And then that could be, this is a little bit clearer to see, because if we were to try to guess the tangent slope, where did I put my ruler? No, it's see-through. It was right in front of me. If we try to guess the tangent slope at this side, we would say it's going to be 0, but it doesn't quite match with this one. The main thing is the hole, and that not existing. So let's talk about what are we talking about next? Oh, okay. Let's talk about some atypical functions, right? So, for example, they want to find where a function is not differentiable, and they're using the function f of x, or f of x is equal to absolute value of x minus 2 plus 3. Let's go ahead and graph this. So, we got f of x is equal to absolute value of x was plus 2? No, minus 2, and then plus 3. All right, so we're going to do this on our calculator. I'll just turn this on. All right, and then we'll do the function of absolute value of x minus 2. So x minus 2 in parentheses and then plus 3. All right, so absolute value of x minus 2 plus 3, we'll go ahead and graph this. Okay, and we can see what it does right here. So what we can see here is we can clearly see the corner right at that point. All right, if we needed to, we could trace it. All right, and we see that it's about 2, 3, or we can know that from understanding the graph. Or if we wanted to trace it x equals 2, we could just type in 2, and we get, whoops, I pressed the wrong button. So we hit trace, and we just type 2 for x. We get 2, 3 for our x values. We know that point. So there fails to be a derivative at 2. Now let's talk about... okay, so this paragraph sums it up pretty well. So if you want to bookmark this page, this is a great definition of differentiability, right? So for differentiable functions, their graphs are unbroken, smooth, with a well-defined slope at each point. Polynomials are differentiable, rationals, as are rational functions, trigonometric functions, exponential functions, logarithmic functions. Composites of differential functions are differentiable, and so are the sums, products, integers, powers, quotients, and differential functions were defined. So all this is saying is that polynomials, rational functions, so functions of rational numbers, trig functions, so sine, cosine, tangent, cosecant, and then exponential functions and logarithmic functions are differentiable, as are the additions of those functions, the multiplications of those functions. So f plus g, f of g, f times g, f divided by g, all of those composites are also differentiable. Right? Now, when they say differentiability implies local linearity, they're talking about the tangent slope. So if a function is differentiable at a point, then that implies that there's a locally linear or a local tangent slope that you can find, or local straight line that we can find at that point. So more or less the example that I was doing with the ruler is what that's talking about. Let's talk about, we're going to skip this. Yeah, if you want to do this exploration on your own, it's pretty self-explanatory. It's kind of cool to see, but I'm going to skip that. Let's talk about derivatives on a calculator. So now we got to learn some new buttons on a calculator, and that is the numerical derivative. Now the interesting thing is we just found out that if we were to do f of x is equal to absolute value of x, it is not differentiable at 0, right? So what's going to happen is we're going to calculate what's called a numerical derivative. Numerical derivatives are actually a formula that you learned in the advanced math book, and it's this one right here. It's the f of x plus h minus f of x minus h over 2h. Right? So that was a formula from the green advanced math book. You probably calculate it hundreds of times. We'll calculate this once, and then we'll show what it looks like on the calculator. So yeah, we'll go ahead and use this example. So we've got the graph of x squared, and then for the value of h, we have to use some infinitesimally small numbers, right? So if we did f of x is equal to x squared, so we know this one will be differentiable. And then for our infinitesimal small numbers, the book says 0.001. I'm going to use 0.001. Wait, no, yeah, sorry. The book says only 10. I'm going to use 2. And using 1,000th is usually a good number to use, right? Now, this is something that some people have called them engineer's method, because we're just kind of cutting and trying small numbers to see what happens. But once we plug that into x plus h, right, and we want to calculate this at 10, right? So I'm getting ahead of myself. So some book notation. If they want you to calculate a numerical derivative, your book is going to say n, hopefully in a better colored marker. Your book is going to say ender, like N-D-E-R. Right, and then we'll see later in your calculator calls it n deriv, right? Same thing. So ender, n deriv, same thing. We're not doing the calculator version yet though. So the book will say calculate ender f of x equals x squared comma 10. What they're saying comma 10 is at the point or the value of 10. So this funny thing is it's more like them saying calculate f of 10. Sorry, calculate f of 10 of x squared. I'm not sure why this isn't the notation that's stuck, but it's not the one that everyone uses. So calculating ender f of x squared at point 10. So that's what this is more or less read as. So when we do this, we've got 10 plus 0.001, since it's squared, and that'll be squared, and then minus 10 minus 0.001 squared, and then that'll be over 2h, so over 2 times 0.001. Okay, so this is how we calculate a numerical derivative. And the funny thing is numerical derivatives can actually be inaccurate sometimes because they work in positions where you'd have cusps or corners and stuff like that. So as we compute this, the denominator is just, why do I keep trying to use this blue marker? The denominator, wow, that's kind of light too. I know, red will save us. Let's go with, so, wow, I completely lost my point. So 2 times that is going to be 0.002. This squared is just going to be 10.001 squared, and then it'll be minus 9.999 squared, right? And then we can compute this in our calculator. This is not the calculator method of using numerical derivatives. Whoops. This is just how we would calculate it. So then we type in 10.001. We'd square that. We end up with that number. And then we'll subtract 9.999 squared. And we end up with 0.04. I'm not sure if you guys, there you go. Now you can see it. So we just calculate that on our calculator. Our numerator is 0.04 over 0.002. Let's go ahead and divide those. Divided by 0.002, and I get 20, right? So it's telling me the numerical derivative is 20. Now let's talk about how to do this exact same thing on a calculator, right? So on a calculator, or on your TI-83 or TI-84, your Texas Instruments calculator, you're going to press the math button, and then you're going to press the number 8, and it's going to give you end derivative. The reason why we're pressing the number 8 is because if we didn't, we'd have to press the math button and then scroll all the way down to item number 8, which is end deriv. So we'll just hit math 8. Whoops. So math 8, that gives me end deriv. Now, what I'm going to do next is I'm going to more or less type in this notation with an extra piece in the middle, because calculators are kind of funny. So we're going to do the end derivative of x squared. Then I'm going to put a comma, right? Comma button's right here above the 7. So I've got end deriv x squared comma. Now I'm going to pick which variable this x is for, which is kind of funny because you're almost always going to use x variables. So you'll then press x again, and then another comma, and then you'll put in the value of 10. Closing parenthesis, calculate the end derivative, and we got 20 as well. Okay? So that's how you calculate end derivatives on your calculator, or numerical derivatives. Okay. How long is this video? 17 minutes. All right. Maybe this is a good stopping point for the first half of the section. We talked about what derivatives are. That's it. That's the end. We don't got to draw any more stuff. Don't forget f of x plus h minus f of x minus h over 2h. I don't think I wrote that properly. This is x plus h. This is x minus h. This is 2h, right? You should have that memorized. If not, memorize it now.